Hi, welcome to video 8.5c, Introduction to Logistic Growth. So before we get into logistic growth, I just want to remind you, because you'll need it for the AP and the DNS, if you'll come across these. I want to talk about regular exponential growth and decay and bounded growth and decay, just so you'll have a reminder of what we're talking about. So if you remember from last year, section 6.2 was exponential growth and decay. So remember, the wording would say that the rate of change of the quantity, for example, the population of a city, the rate at which the population is changing is directly proportional to the population of the city. So that's dy dt equals ky, and after the very long process of solving that differential equation, we ended up with y equals y0 times e to the kt. y0 being the initial amount you start off with, t is how much time has passed, k is a constant, and y is the final amount you have after that amount of time has passed. So here's me showing you how to solve that. That will give you ln y once you separate the variables. Get rid of the ln, that's e to the power of, and then the tricky part is actually breaking this quantity up into e to the c1 times e to the kt, because remember, if you multiply two things with the same base, you would add their exponents. E is a constant raised to an arbitrary constant. That simply becomes another arbitrary constant, and rather than calling it c, we call it y0, because if I take this equation and replace t by 0, I will get y equals c times e to the 0, which is c. So it turns out that c is the final amount at time 0, meaning it is the initial amount. It is important to know what these graphs look like. For exponential growth, at time 0 you have an initial amount. It could be 5, could be 2,000, could be 0. And then of course it's y equals a positive number times e to the k times t, and of course being growth, it is rising with time. As far as decay, you'll start at that initial amount and it will decay. Now the amount of stuff you have cannot be negative, so it doesn't matter what we're talking about. It'll decrease, but it will decrease and approach a horizontal asymptote. Okay? Alright, so then we also in AB saw bounded growth and decay, and that's when you have a maximum value that you cannot go beyond. If you solve this differential equation, which I'm not going to bother showing you the whole process, you get the following. So you get y equals a minus b times e to the negative a kt. So here what happens, your initial amount, of course, if I replace t by 0, e to the 0 is 1, I have a minus b times 1. So my initial amount is a minus b. And what happens is it's going to grow, but you're noticing it's not growing exponentially the way the last one did. It's growing concave down. And the reason is because this is e to a negative exponent. So what happens is it will grow, but what it will do is have a limiting value, it's called. In other words, it'll only grow insofar as it cannot get beyond the maximum value of a. So as you can see from the graph, the limit as t goes to infinity is this quantity a, and you can actually plug in t is infinity. You'll get e to the negative infinity, which is 1 over e to the infinity. Of course, anything over e to the infinity is infinity, and b over infinity would be 0. So you can actually algebraically confirm that fact. So, again, this equation will look like this. And this is like Newton's law of cooling. This is bounded decay instead of bounded growth. And of course, you take a pie out of the oven, it's at a certain temperature. As time goes by, the temperature of the pie will drop, and what it will approach is the room temperature. It's never going to go below the room temperature. Okay, so now we're looking at logistic growth, different type of growth. So here there often exists some upper limit L past which growth cannot occur. In such cases, you assume the rate of growth to be proportional not only to the existing quantity, but also to the difference between the existing quantity y and the upper limit L. that is dy dt equals k times y times L minus y. In integral form, we can write it this way. They simply separated the variables. They put the y's on one side and the t's on the other, and then they take the integral of each side. So, I'm going to show you this on the next page, but when you solve this differential equation, you will get this equation. And you do want to memorize this, because unless they actually ask you to show the derivation or just show the solving of the differential equation, you can jump directly from here to here. Now, the graph of logistic growth is really interesting because it grows the whole time, but you'll notice in our other cases it was either concave up the whole time for exponential growth, or bounded growth, it was concave down the whole time. Here it's concave up, and then it becomes concave down. And a perfect example in real life of logistic growth is the spread of disease or the spread of a rumor. So what happens is you start, with the first person who hears the rumor, everybody starts telling everybody, so very quickly a lot of people know, but then it gets to the point where you try and tell someone the rumor and they've already heard it. So there's fewer and fewer people to inform about the rumor. And if the school population, say, is 1,000, obviously if only 1,000 people are on campus, you can't have 2,000 people hearing the rumor. So it will approach that 1,000. Keep in mind, A is that maximum amount, the maximum population of the school, city, town, whatever. B is also a constant, which you will be able to find. K is also a constant, which you'll be able to find. E is, of course, a known constant. And our equation is the real variables are y, which is the final amount, the final number of people who will have, the amount of people who will have heard the rumor after t times. So t and y are our two variables. Okay, so here's showing how to solve this differential equation for logistic growth. For me, it would be a bonus question, but for the AP, once in the past, it's actually been a free response, like part A, show the word to solve a differential equation. So I separate the variables. And then, of course, the reason it's in this section is because in order to integrate this, you have to do partial fractions. So coming over here, here's my denominator. So I have these two single denominators, cross product. You're going to let y equal a so that this term becomes 0. You'll get f equals 1 over a. Keep in mind, a is a constant, and in an actual problem, you would know what a is. That's the maximum population, the population of the school, the city, whatever. And then we let y equal 0, and that'll get rid of this term, and that'll give us e is 1 over a. So I take this fraction, replace e and f by 1 over a, I'm over here, and then I integrate, I get these ln's, factor out the 1 over a. On the right, of course, I'm integrating a constant dt, like if it was 3 dt, the answer would be 3t plus c1, but it's k. Okay, then we use, now this is an interesting one. You wouldn't think of doing this, but they actually pull the negative on the outside and change the order of these, just convenient for them. Then they rewrite this using the quotient property of logarithms. Then they get rid of the ln. Then there's that tricky part where you break this up into e to the negative akt times e to the negative ac1. This, of course, is just a constant because it's the constant e raised to a negative, the constant a, the maximum population, and c1's an arbitrary constant, so we call that constant b. Then I do a cross product so that I don't have any more denominators, and then I isolate my a by sending y to the other side, and finally I isolate the y. So that's how we get there. So what you want to know is if you have a differential equation where the rate of change of the quantity is proportional to the quantity and a difference between a limiting value and the quantity, you can go directly from here to there. Okay?